Hello everyone. Imagine a situation where a patient arrives at a hospital with a suspected bone fracture. Doctors rely heavily on X-ray images to determine the type of fracture, but analyzing these images require time and significant expertise. What if an AI system could assist doctors by instantly analyzing X-rays and identifying the fracture type? This is exactly what our project focuses on. In this project, we developed a deep learning model that automatically detects a bone fractures from X-ray images. For this project, we used Python, PyTorch for building neural networks, OpenCV for image preprocessing, and Google Colab for GPU accelerated training. Using GPU significantly speeds up the training process compared to CPU. We used a medical X-ray dataset for binary classification. The dataset is divided into three parts: training set, validation set, and test set. Training data is used to train the model. Validation data is used to tune the model during training, and the test dataset is used to evaluate the final performance. Each image belongs to one of the two classes, fractured or non-fractured. Data preprocessing step. Before feeding images to the model, we performed several pre-processing steps. First, images were resized by 224 by 224 pixels, which is the standard input size for many deep learning models. Next, we converted the images into tensors and normalized them so that the model can learn more efficiently. We applied some data augmentation techniques such as horizontal flipping, vertical flipping, etc. These techniques help the model generalize better and reduce overfitting. Now we move on to the model architecture. In this project, we implemented a hybrid deep learning architecture that combines multiple powerful techniques. The model consists of three major components: CNN backbone, a convolutional neural network extracts local features such as fracture lines, bone edges, texture patterns, X-rays, etc. etc. Then we use Vision Transformer, VIT. The Vision Transformer analyzes the global structure of the image and captures relationship between different regions. Then we use Vision Mamba. Vision Mamba efficiently models long-range dependencies, allowing the model to connect patterns across distant parts of the X-ray image. By combining these three components, the model can understand both local details and global structure, which improves fracture detection performance. Next, we move on to the training process. The model was trained using the following settings. Loss function was the cross entropy loss, and optimizer was Adam. Learning rate scheduler was cosine annealing. During training, the model processes the images in batches and updates its weights using backpropagation. We trained the model for 10 epochs, meaning the model saw the entire dataset 10 times. During each epoch, we monitored training loss, training accuracy, as you can see in the given Google pull. Training results. During training, we observed that the loss decreased significantly while accuracy increased. The model achieved a training accuracy of approximately 99%, indicating that the model learned strong patterns from the dataset. However, high training accuracy alone is not sufficient. So we evaluated the model using validation and test dataset. Now we move on to the model evaluation part of the project. To evaluate the model performance, we generated a confusion matrix. A confusion matrix shows true positives, true negatives, false positives, and false negatives. And these helps us understand how well the model distinguished the fractured and non-fractured parts. As you can see the confusion matrix on the screen. This helps us understand the actual actual correct predictions made by the model on the test dataset. We also calculated important metrics such as accuracy, precision, recall, and F1 score. These metrics gave a complete view of the model's performance. Then we move on to the random X-ray prediction demo. In this step, we randomly select a X-ray image from the dataset. In this step, we randomly select a X-ray image from the dataset. The model then predicts whether the bone is fractured or not. We display the input X-ray image, the actual label, the predicted result. Explainable AI. One of the most important aspects of medical AI systems is explainability. To understand how the model makes decisions, we use the technique called GradCam, which stands for Gradient Weighted Class Activation Mapping. GradCam generates a heat map highlighting the regions of the image that influence the model's prediction. In the heat map, red and yellow regions show where the model focused its attention. For fracture images, the heat map highlights the fracture region of the bone, confirming that the model is learning meaningful medical features rather than random patterns. Applications of the model in the AI industry and the healthcare industry. This system can be used to assess doctors in various ways. Firstly, early fracture detection, then reducing the diagnostic time. That is very important nowadays, supporting medical decision making. However, it should be used as a support tool for clinics, not as a replacement for professional diagnosis. I would like to conclude in the following way. In conclusion, we successfully developed a deep learning model capable of detecting bone fractures from X-ray images. By combining CNNs, vision transformers, and vision mamba, the model can capture both local and global patterns in medical images. We also incorporated explainability techniques such as GradCam to ensure transparency in model decisions. This approach demonstrates how AI can assist healthcare professionals and improve diagnostic efficiency. Thank you for your time. I would be happy to answer any more questions that you may have in the offline presentation. Thank you.